All right, today is Monday, March the 20th. This is AP Chemistry. Today we're going to be talking about salts, the acid-base nature of salts, and buffers, the pH of buffers. And ideally we're going to then get into mixing and doing titrations of acids and bases. All right, so first off, when we're looking here, this is just the review. So when I want to look at which of the following has the highest pH, when we say highest pH, what am I looking for? Acidic, basic, or neutral salt? Basic salt. So which one of these salts is going to be basic? B. Does everybody understand how and why B is the basic salt? Strong base, weak acid. Okay? So which part of this is going to react with water? The CO3 2-, and this wasn't part of it, but how would the CO3 2- react with water? It's going to do what? Take one hydrogen to make HCO3- plus OH-. So it's a base according to Bronsted-Lowry because it's going to accept a hydrogen from the water. It's a base according to Arrhenius because it produced the hydroxide ion. Bases, the definitions don't contradict themselves. They're just different perspectives of the same reaction. Okay? If you can't remember one definition, just know that, okay, it made OH-, so it's got to be a base. Okay? So, when solid ammonium chloride is added to pure water, the pH, again, what type of salt is that? An acidic salt. So what's going to happen to the pH? It's going to go down. Okay? Because the action of which of the ions? The NH4 plus. So that is going to be, the answer becomes less because of the reaction of NH4 plus with water. Right? Are we good with that? So notice how these are very, very similar. Okay? Which salt will hydrolyze water, produce a basic solution? A. What type of solution is this going to make? NH4I. Acidic. What about SrNO3 Neutral. What about this C2H5? This is ethylamine, so this is the ethylammonium ion, ethylammonium bromide. Okay? This is going to be acidic. This would donate. What's going to be the charge on this whole thing right here? The C2H5NH3 is going to be plus, and then with a Br-. And that plus, that whole thing is going to react with water. Since it's an acidic salt, it would donate the hydrogen, which we'll actually see down here. So, K2SO3, is that acidic, basic, or neutral? Basic. So what part's going to react with water? The SO3 2- plus water is going to make what? HSO3- OH-. Are the charges, if you don't have the charges on there, it's wrong. If you don't have the charges correct, it's wrong. Okay? So, does everybody see how to do this? So NH4Br is what type of salt? Acidic. So which part's going to react with the water? And since it's acidic, what does it do? Donates the hydrogen, so you're just going to get NH3 plus H3O plus. Now the order that you put it doesn't matter. You can put H3O plus NH3. That doesn't matter at all. Okay? Now, what about BaCl2? Neutral. So does it react with water at all? No. You put it in, it would dissociate into the ions, Ba2 plus and 2Cl minus, but neither one of those are going to react. They're not going to hydrolyze. They're not going to break the water apart at all, react with water, do anything. And then C6H5 NH3Br is what type of salt? Acidic. So it's going to be the C2H5 NH3 plus reacting with water. Just like this one, all of your amines are going to do the same thing. They're going to donate make C2H5NH2 plus H3O plus. Are we comfortable with that? All right, because we struggle with that on the quiz. So hopefully we're correcting some of our misconceptions, filling in some blanks, figuring out how to do that. And that's why the charge goes down, because you're donating an H plus, so you're getting rid of a plus. So you're always, and sometimes you have to remember when on a number line, you go from +1 to 0 to -1. You got to remember there's 0 in between there. You don't go from +1 to -1. Okay, you go through 0. All right, now we get to the problem. Wasn't there a problem on the bottom of this? Okay, there it is down the bottom. Hey, Anthony, move that down to show the problem, please. Move it a little bit more so it's higher up. Perfect. Okay? So now it says sorbic acid is a weak monoprotic. Monoprotic meaning just donates one of the hydrogens. It's got all this on here, but it's just this hydrogen. And again, it's going to be, what's going to be the functional group? Since this is a hydrocarbon, what's going to be really be on the end of that sorbic acid? What's the acid group for any organic acid? Okay, what did he say? And what's somebody else? What's a carboxylic acid? Okay? Yes, he would. Okay, so this is one of your carbons. This is the H that's out in front. That's this H right here. This is the ionizable H. Then we just have your carbons, ... all the other stuff to make difference between lactic acid, sorbic acid, acetic acid. It's just how many carbons, with the carbon chain that's over here attached to it. But all of them are going to have this carboxylic acid group. Okay? And so this hydrogen gets donated, and so you end up getting the H3O plus with the water, and then you have this left over as a minus with the extra electron. Now once it loses that, what special phenomena can that carboxylate ion make? Resonance, because now the double bond could be here or there. And that stabilizes the ion, which helps the hydrogen, makes it easier for that hydrogen to leave. Okay? So but all organic acids have this carboxylic acid group. Okay? So anytime we have lactic acid, acetic acid, sorbic acid, propionic acid, it doesn't matter. It's just how many carbons are in the chain, but it's always going to end with COOH. And oxalic acid is just two of these put together. Oxalic acid is just this. Okay, so it's just two carboxylic acid groups linked together. It's diprotic. And where is it? C2. Notice oxalic acid right there. It's 5.9 times 10 to the minus 2. It's the strongest weak acid. Okay, for the first losing one hydrogen, the Ka1. Yeah. That's the oxalate. The C2O4 is the oxalate. All right. So, sorbic acid is a weak monoprotic acid with a Ka of 1.7. Its salt, potassium sorbate, is added to cheese to inhibit the formation of mold. All of that is very nice. Okay. What is the pH of a solution containing 11.25 grams of potassium sorbate in 1.75 liters? So, what is going into water? Are you putting any of this into water? No. We're putting the salt into water. So what type of salt is this going to be? A basic salt. So which part of this salt is going to react with water? So the big old long complicated part. So the sorbate part. C6H7O2. What's the charge going to be on it? Minus. It's the second one. It's potassium sorbate, so it's the second one, so it's minus. Plus water. Since it's a basic salt, what's it going to do with hydrogens? It's going to gain hydrogens. It's going to produce which ion? OH minus. Okay, so we identify it as a basic salt, but then we need to translate that into our equation. So we're going to get HC6H7O2 plus OH minus. Now, we have to figure out the concentration. 11.25 grams divided by, what's the molar mass? 150.1 grams per mole divided by 1.75 liters. And that all comes out to equal 0.043 molar. Okay? So that's my initial concentration. 0 and 0. But this is a base. What's the purpose of the first line? Because it tells us Ka. This is the acid. This is the conjugate base. So I need the Kb, which is going to equal Kw over Ka. 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 5. What's that come out to? 5.88 times 10 to the minus 10. So that's equal to my Kb, which is going to equal x times 0.043 minus x. But again, this is 10 to the minus 2, 10 to the minus 10, so what can we assume about x? Negligible, so you write that out to the side. So x is equal to my OH minus, which is equal to the square root of 0.043 times 5.88 times 10 to the minus 10. That equals 5.02 times 10 to the what? Negative 6. Okay, that's my OH minus. So the POH is equal to negative log 5.02 times 10 to the minus 6, which is equal to 5.3. We should have, technically, since this is 3, we should have 3 decimal places on our pH, but 5.3, what's the next one? 5.29? Okay, 5.290. Okay, so therefore pH is equal to 8.71. All right? So, once again, think about what's actually going in. We don't need to write the acid isn't what is going into the water. We're putting in the potassium sorbate, the salt. The purpose of giving us the acid information is so we can get Kb. Now, notice on this problem that we're only putting in one thing. We're only putting in the salt. Because when we go and look at this one that I put on the board, now it says a student prepares a solution containing equal molar amounts of both the acid and the salt. So now we're putting both things in. But when you're putting in the acid and the salt, what equilibrium do we write? What equation do we write? For the acid, for the salt, do we combine them together? What do we do? I heard someone, Anthony, what? You use the equilibrium of the acid. In a buffer, you're going to use the equilibrium of the acid or the equilibrium of the base. The salt is going to be the common ion on the other side. So this is lactic acid, so it's going to be HC3H5O2 goes to H plus C3H5O2 minus. So this is the equation that we want to use. Now, if we were to go and try and find the pH of this, they would have to tell us how much was put in. But they don't give us any of that. We don't know the Ka values. So we just know the pH of the solution is 3.5. But if I go and add 3 drops of HNO3, where is that going to be in this equilibrium? How is that going to affect it? I'm adding H plus, right? So which way is the equilibrium going to go? Because I have some of this, the H plus can react with it and go left. So what's my net ionic equation for the acid HNO3 reacting with this? Do I need the NO3 minus? No. So it's going to be H plus, that's my acid, plus the base, the X minus, C3H5O2 minus. And what's that going to go to? You just say HC3H5O2. But if it's a base, if I add in some NaOH, what's the NaOH going to react with? But technically it's going to react with this, pull it out, and force it to the right, correct? But when we want to write the equation, it's going to be reacting, it's really going to be pulling this one off. Okay? I like to think of it like this, but when we have to write in a reaction, it's going to be reacting with this. So it's going to be OH minus, again, we don't need the Na part from the NaOH, is going to react with the HC2H3O2. And what will it make? C2H3O2 minus plus C3. 5. That's what I said. I went to acetic acid. C3, Steve. 3. But the reality is none of that matters. It doesn't change anything. So it's just the react opposite. So the whole point of a buffer is that we have some of this and we have some of this. Equal molar. 1 molar, 1 molar. This is my acid. This is the base. So if we're going to react, if I add base, it reacts with the acid. If I add acid, it reacts with the base. It's because we have equal amounts of both that it can handle adding acid or base to the solution without the H plus changing significantly. Okay? So we need to be able, this was on the last 2 years. 2 years ago was in a multiple choice question, last year was on a free response. This actually is a modification of the free response question from last year's test. They only asked part A, and they just changed the acid. Okay? So we need to be able to do that. Now, how do we find the Ka? Well, we can use the Henderson-Hasselbalch equation. Yes, because pH is equal to pKa plus the log of C3H5O2 minus over HC3H5O2. But if it's equal molar, this is 1 to 1, right? What's the log of 1? 0. Therefore, pH equals pKa. What's the pH? 3.5 is equal to pKa. What does P mean? Well, so what do we need to do? So Ka is equal to 10 to the negative 3.5. Wesley? Times 10 to the minus 4 would be your Ka. All right? That's kind of a review of everything that we've kind of done up to this point. The pHs, okay? So, given that this is 10 to the minus 4, okay? If we want to push this to where it's 50% to where we have a 50-50. So it's 50% ionized. I couldn't think of the word ionized. Okay? Do I want to add acid or base to this to push it to the right? Base, right? We just said base is going to push it to the right. If I add H plus, it's going to push it that way. So I need to add base to it in order to keep it here. So anything here, this pH is already at 3.5. So anything that's a pH of 4 or greater is going to push it, at least because I know at 3.5 I have a 50-50 mix. Right? So anything above a 3.5, 4 up, is going to add base, is going to push it this way. So you just look at the pKa. Really, you look at the power of 10, which would be a pH around 4. And anything above a 4 is going to push it to the right. Now, if it was a base, okay, if we were trying to deal with it as far as from a base point of view, say we had NH3 plus HOH. I know it's distracting out there, but okay. Now, if I want to push it to the right, this has a Kb equal to 1.8 times 10 to the minus 5. Okay? So what's the pH of this going to be about? pOH is going to be around 5. The pH is going to be around 9, between 9 and 10. What?
I said that 16 minus 5.
Oh. 14. 16 minus 5 is 11, but it's 14.
Wow.
Okay. Okay, maybe we need to practice do our addition tables again. Yeah. Okay? Now, so, the pH is around 9. Now, what do I want to do? If I want to push this to the right, right now it's going to be barely ionized. You're going to have mostly this. Very little of this. So if I want to push it to the right to make sure I get 50%, that's where pOH equals pKb plus this ratio, which is going to be flipped. Okay? What do I need to do? I need to add H plus, right? So I need to have the pH go down. As the pH goes down, it's going to react with this. As I add H plus, it's going to push it to the right. So this time, the pH is 9, so any pH less than 9 is going to make it 50-50 or greater. You circle 9, yeah. Okay? So it's just trying to figure out, it's all based upon this equation. It's the fact that 50-50 makes this one go away. So it's when pH equals pKa is going to be your cutoff, which you just really look at the power of 10. And then just think about as far as if I'm an acid, then I want to have everything above that. I want to add base. If I'm at a base, I need to have everything below it. I need to add acid. Yeah. I mean, that's because it's all based on that. As far as your justification thing? Oh, yeah. I just didn't feel like writing it all over again. In the sample, that is responsible for pH remaining at. That's what these two equations are. Yeah, it's just, again, and if you want to look at, I'll use this book over here. Y'all, these white things, these books, have all kinds of useful information in them. You may have to adjust that for me. Okay, Anthony, just... Okay, now just move the camera. You can tilt the camera to make that go up higher. There you go. Okay, and what page is that, Anthony? Page 729. This is showing the exact same thing that we just talked about. Here's your buffer. Here's your buffer. Listen, ladies. Here's your buffer containing HX and X minus. Okay? So that HX is the acid, X minus is the salt. It's open, I think.
He's just standing there.
Tell him to come in. Wave him in. Come in!
It's open.
You fool.
Come in! Come in! It's open. Come in! I think it's something Hall. Yeah.
Sir Robert Bryson Hall Jr. Sir?
So, once again, HX, listen, now refocus. HX is the acid, X minus is the salt. It's going to be, lactic acid, sodium lactate, acetic acid, sodium acetate. Okay, so we just have, this is the anion from the acid is always going to be the salt. That's the common ion. So, if you add a strong acid, acid is going to react with the base. This is the acid, the basic salt. So, we just show that. If you add a strong base, it reacts with the acid and goes to this. That's exactly the equations that we just did right here for that problem that's on the board. Okay? This is true for any buffer. The acid reacts with the base. Now, what if we had this buffer right here? We had ammonia and ammonium chloride. So now if I add acid to it, what's it going to react with? Well, it's really going to, yes, this, but it's going to react with the base. We're going to have to do the equation here. So it'd be NH3 plus H plus going to what? And yeah, NH4 plus. So if I add acid to this right here, if I have a buffer of 1 molar and 1 molar of this, if I add acid, it's going to react with the base. This is your base. This is your acid. So if I add some base to it, some OH minus, what's the equation going to be? Plus OH minus goes to plus H2O. Just the other direction. Alright? If you have a buffer, you always have an acid and a base. You add acid, it reacts with the base. If you add base, it reacts with the acid. The point of the buffer is that you have some of both, equal amounts of both, so you can add acid or base, and both will react, but the H plus pretty much stays the same. Okay? You might want to read that page in the book. Alrighty. Shoo! Thank God spring breaks in 4 days from now.
I thought we had another.
Nope. Okay. You are? Why? Why? You're playing at Brook Highland? And my wife, you're probably playing the same time my wife's playing.
Maybe I was. When we played, we got there at 2 and we played so much.
Yeah, she was there from 2:30 to 5.
Well, maybe we saw her.
You probably did.
They were late playing. You should phone it and look for
Look for the Pantene hair, guys. Okay. Last thing, no, you don't need to. The last thing that we need to talk about, you can go in 15 minutes. Last thing that we need to talk about now is acid-base neutralization reactions. Okay? What happens when we start mixing the acids and the bases together?
Yes. When will we stop learning for the Friday? Because I just want to know.
For Thursday afternoon?
Thursday. Oh, okay.
No, Thursday morning for us.
He'll probably put up a video with stuff.
Okay. We're going to have 3 scenarios that we're going to look at. Strong acid, strong base. Weak acid, strong base. Strong acid, weak base. But we're not going to do weak plus weak. Okay? And we need to look at what the titration is going to be, how to calculate how much of each one is it going to take to neutralize, and look at what the graphs are going to look like. And be able to calculate the pH at different points during the titration. All that for that? That's how I lose them. Okay, so if I look at HCl plus NaOH, what's that going to make? Thank you. NaCl plus H2O. What type of salt is that? Neutral salt. Strong plus strong makes neutral. Okay? So, if the question says, how many milliliters of 0.1 molar NaOH are needed to completely neutralize .25 milliliters of 0.25 molar HCl. What do I know is true at the neutral point? H plus is going to equal OH minus. Not necessarily HCl equaling NaOH. In this case, it's 1-to-1, so that would be true. But H plus equals OH minus. So if I was just to do this stoichiometrically, all right, I am going to go, how do I convert 25 milliliters of 0.25 molar to moles? How do you convert molarity to moles? Multiply by liters. Molarity times volume always equals moles. Right? So, y'all listen. Too much talking. This is where we're going to just focus. 10 minutes. 0.25 moles per liter times my 0.025 liters. That's going to give me moles of HCl. Okay? But I don't need to stop there. Times, what's my mole ratio between the NaOH? 1-to-1, so it's 1 mole of NaOH for every 1 mole of HCl. And this is liters of HCl. Okay? So my moles of HCl cancel. So now how do I go now to volume? I have molarity of NaOH. How do I find milliliters? I need moles on the bottom, right? So I'm going to say 1 liter over 0.1 moles. So that's going to tell me how many liters of NaOH I need. So we can end up just multiplying all that out, and we get 0.0625 liters, which is equal to 62.5 milliliters. So if I want to neutralize my 25 milliliters of 0.25 molar, I'm going to need 62.5 milliliters of the base.
You would just do 0.25 molar times 25 milliliters equals 0.10 molar times.
Yeah, where I'm getting there. Okay? But I wanted to show you stoichiometrically first. Okay? Because there is one issue when it's not 1-to-1. So, what Reese is saying is, can we not just simply use an equation that, for acid bases, molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. MAVA equals MVVB. It's a lot simpler as far as calculating how many milliliters you need to titrate. Now this is only true for 1-to-1 ratios. One-to-one acid-base reactions. So what if we change this to H2SO4? Okay? So what's going to change here? The mole ratio is going to be 2 moles of H2SO4. So we're going to divide everything by 2. Okay, so because we get twice as many hydrogens here, okay, did I put the ratio in the right spot? Yeah. Okay, so what is that going to mean? Well, that's what I'm saying. Do I have it backwards? Because it should be on top. Okay? How many milliliters of 0.1 are needed to completely neutralize 25 of H2SO4? Okay? But, that's right. So we're going to have a 2 there. I knew it was wrong. 2 moles of NaOH. Hey, when all else fails, balance your equation. Okay? We'll get 2 waters as well. We're going to get Na2SO4, but that's totally moot. Okay? But, when we look at this equation now, so now the 2 is up here on the NaOH. So when we do this, you're going to end up needing double the amount, which is, what is that going to be, 13.135? 125? Man, my brain today. Liters. 125 milliliters. But where does that 2 go in this? Okay? Because the reality is what this is telling me is that moles of H plus is equal to moles of OH minus. It's not moles of H2SO4 equal this, because they don't. But at the neutral point, it's moles of H plus equals moles of OH minus. So, for every 1 mole of H2SO4, we're getting 2 moles of H plus. So the 2 actually is going to go here in our equation, if we want to use the MAVA. Now, if you do it in terms of stoichiometry, assuming you balance your equation first, it works every time. But when you want to use MAVA and you have a diprotic or a dibasic substance, the 2 is going to go based upon this 2, not that 2. It's moles of H plus and moles of OH minus. So if it was a BaOH2 here, plus HCl, now the 2 is going to go in front of the base. The 2 would go here.
But that coefficient is going to be good. It's just going to multiply something else.
But if you're putting it into this equation, it's going to go there.
Yes, you put the coefficient on the side.
but I'm telling you, people are going to get confused because if you have the 2 in front of the HCl, they're going to want to put the 2 in front of the acid side. Okay? So I'm trying to show you is that the 2 is the result of that subscript 2. That's where you put it into this simplified equation. Now, if you do it stoichiometrically, you just do it like we always do. Put what the coefficient and the mole ratio right here. You just kind of go down the line. You just use the molarity as your conversion factor between liters and moles. Okay? So it's a very simple process to figure out the volume needed to neutralize. Okay? Now, what would this graph look like? This is milliliters of, let's titrate, we're looking at NaOH into the acid, milliliters of NaOH added. Let's go back to our original equation of HCl. Okay? This would be pH. We're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 3, 5, 7, 9, 11, 13. So there's my pH, milliliters of the 0.1 molar added. So if I start with what we started originally, HCl plus NaOH, NaCl plus H2O. Okay? If I have 0.25 molar HCl, where's my pH going to be? Near? How low? How do I find the pH of a 0.25 molar solution of an HCl, strong acid? Just take the negative log of 0.25, right? And it comes out less than 1, greater than 0. Correct? 0.6. So that's where my graph's going to start, at 0.6. Okay? So then I'm going to begin adding it in, and the pH is going to come up and it's going to go here. And how many milliliters did we say we had to add? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So 62.5 is going to be somewhere right around here. Might want to be looking at it when I do that. Okay? So that's somewhere right around your 62.5. So what's going to happen is that we're going to get a relatively straight line, and then it's going to go up perfectly straight almost to here. And then we're going to find right here is going to be the middle of this steep part. I got to make the middle. Okay? Is right here at pH 7. I know I'm going uphill, but that's where it's going to be. Okay? On a real graph. For a strong acid, strong base, since the salt that's produced is neutral, there's going to be this sudden increase. Once all of the acid gets used up, then we're going to get a sudden increase in the pH, and the middle of that vertical line is where your exact equal neutral point is going to be. And so this is your equivalence point. Right at the 62.5 is where it's going to be, right at 7. And this is almost vertical. There might be just a hair lean to the right. Okay? So we're going to get this titration curve. It's always going to look like this. So the equivalence point, the pH at the equivalence point of strong and strong is always going to be 7, because at the equivalence point you don't have any of this left. You don't have any of that. They're exactly equal. They've completely reacted to one another. We have all of this. And what type of salt is that? Neutral, so the pH is going to be 7. Now, why does the pH keep going up after I get past the equivalence point? Because now I'm having excess base, and it's strongly basic, so it goes up rapidly at that point. Okay? Tomorrow we'll look at what happens if we do a weak acid and a strong base, or a weak base and a strong acid. And what's going to happen is we're going to be making a buffer as we're titrating. So we're going to have to find the pH at different points.
We're going to do a lab.
Yes, but probably after spring break.
Could you not just, on that equation there, could you not just say the coefficient of the base?
You can say whatever, however you want to say it.
Like
Okay?
you don't have the
Yeah, I mean, you don't have to explain the equation. You just have to use it right.
Okay.
I know, it's really bad that so many people are going to be out on Friday.
It's just, not just,
Choir people and HOSA.
what's the rest of your going?